Welcome to the chapter on math. You may be wondering why we're covering math in the 9th chapter of this program. You might expect that because math is foundational that it would be covered earlier. But the reason I've done it this way is, in my opinion, there is a fair amount of math to cover, and I find that candidates sometimes get burned out or bored covering all this old math that they may have forgotten from a long time ago before getting into the really juicy engineering topics. So I believe I addressed this earlier in the program, but I wanted to mention it again here. There's a reason why we dive right in with thermo and fluids and dynamics and mechanical design and so on, because we really want to focus on those core engineering topics. And in all honesty, the only math that most of those topics really rely on is algebra. And most engineers already have a pretty good algebra background because they did so many levels of math. If you did algebra 2 and geometry and trigonometry and multiple levels of calculus at any point in the past, even if you're not great at some of those later courses like calculus and onward, chances are you got enough reinforcement of your algebra skills that rearranging equations and things of that nature is not going to be a huge deal for you. So hopefully if you're doing this program in order, you've found that you have enough of a math background that nothing we've done up to this point has been too rigorous mathematically. And now we have the opportunity to get into the detail. And if you get pure math problems, whether they're from the realm of geometry, trigonometry, algebra, calculus, even things like matrices and transforms and differential equations we'll cover toward the end. And of course, if you're someone who feels strongly about starting with math because you feel like you don't want to move forward until that foundation is absolutely established, then you're welcome to start with this section, even though it's showing up in chapter 9. You can do it first and then circle back at the beginning and go through from there. So let's get started with lines. A straight line has a constant slope. So if we draw our coordinate axis, x and y, and I'll draw an arbitrary line here. I'm starting my line at the origin. That doesn't have to be the case. It could have some y-intercept where it crosses the vertical axis above or below the origin, but I'm going to start there. And then if we draw two arbitrary points on that line, and we define those points as having an ordered pair coordinate of x1, y1, and x2, y2, then we can define the slope as the rise over the run. And if the run is 1, then the rise will be m. So the slope is rise over run, so m over 1. Or said differently, we can say that it's the change in y, the change in the vertical, divided by the change in the horizontal, because the rise is the change in the vertical. So if we were to map these points over to the left with horizontal lines, then we could define that difference as delta y. And the same, if we drew vertical lines down to the horizontal axis, we could locate the x-coordinates on the x-axis, and we could define that distance as delta x. And the slope then would equal the change in the vertical, delta y, over the change in the horizontal, delta x. Or to drill down on that even more, we would say y2 minus y1 divided by x2 minus x1. And now you might be wondering, what about the order here? Is this arbitrary, or does it matter what order you put these in? It's usually written like this, but it is arbitrary. You can do y1 minus y2 instead of y2 minus y1, but you do have to be consistent. So whichever one you start with in the numerator, you have to start with the same one in the denominator. Otherwise, you'll get the opposite slope. Whenever we have a line that's going up and to the right, it's going to have a positive slope. When we have a line that's going down and to the right, it's going to have a negative slope. That's pretty easy to remember because you can just think about reading. We read left to right. So if you're going up the hill, then that's a positive slope. And if you're going down the hill, it's negative. And then a good thing to know, which is in the reference handbook, but I'm mentioning it here as well, I think it would be helpful to remember, is that for a perpendicular line, which is a line that makes a 90-degree angle with another line, the slope is the negative reciprocal. So for instance, if we draw this line that we already drew, we'll call this line 2. And if we draw a separate line, I'll call it line 1. Let's make it perpendicular. This would be our line 1. We would say that the slope of line 1, m1, would equal negative 1 over m2. So it's the negative reciprocal, or inverse if you like to think of it that way. So even if you don't know the slope of a particular line, if you know it's perpendicular to another line and you know the slope of that other line, then you can use this to figure out the slope of the line you care about. The equation of a line can be written in 3 different forms. The first form is the standard form. And this is the one we work with the most, and it's the one that's most useful for graphing. And it says that y equals mx plus b, where m is the slope and b is the y-intercept. So this line that we drew here would have a slope that's positive. I don't know exactly what it would be. Maybe it would be somewhere between 1/2 and 1, let's say. But since it goes through the origin, the y-intercept would be 0. If it crossed the y-intercept above the origin, then the y-intercept would be positive. If it crosses below the origin, then the y-intercept would be negative. And the only things you need to graph a line are the slope and the y-intercept. So if you know the value of m and you know the value of b, then you can say that that equation is fully defined and you're able to graph it. If you actually do want to make a graph, since we don't have graphing calculators for the exam, we only have scientific calculators, you can actually make a table of values. You can pick values for x and then calculate values for y using the equation of the line. And you can literally just plug in numbers 1, 2, 3, 4 and onward and figure out what the corresponding y values would be. Those are ordered pairs, which represent points in a 2D plane that you can plot and then connect them. So that's the standard form. The next one is the general form, and we tend not to use this one a whole lot, although you may have a problem statement that gives you the equation in the general form. Usually we're going to change it into the standard form, especially if we want to be able to graph it. And the general form is a times x plus b times y plus c equals 0, where a, b, and c are constants. So if you wanted to get this by itself, you would subtract ax and c to the other side. You would divide every term by b, and then you'd have y by itself. Once you have y by itself, and on the other side of the equation you have some constant times x, that constant is m, that's the slope, and then that may be plus or minus some constant b, which is the y-intercept. So usually we find ourselves going from the general form to the standard form. Unless the answer choices are in the general form for some reason, then we may have to go back in the other direction. And the third form is the point-slope form. And the point-slope form is useful for finding the equation of a line in standard form when you know two things. You know the slope and the location of one point. So we said a line is fully defined if we know the slope and the y-intercept. The y-intercept is a point. But what if we know some other point and the slope? Well, the line is still fully defined, but it's not in standard form. So what do? We use this equation. It says y minus y1 equals m times x minus x1, where x is our independent variable, y is our dependent variable, and x1, y1 is the location of this point that we know. It's the ordered pair of the known point. And the slope is also known. So we're able to plug in m, x1, and y1. And the only unknowns are x and y. So then we can rearrange that. We can distribute m. We can add y1 over. We can combine like terms. And then eventually we'll have a standard form equation of a line where it's y equals mx plus b. So usually point-slope form is not a final state. It's something that we're doing as an intermediate step to get into standard form or general form. Again, we can toggle between these two, but it's unusual that we're going to put it in this form and keep it that way. And one more somewhat related topic I thought we would hit while we're talking about lines is the equation for the angle between two lines that intersect. So for example, you'll find this equation in the reference handbook, but they don't draw a picture. So it's a little bit odd to have the equation there and not know how to apply it without being able to think about what's actually happening. If you have two lines and those lines have different slopes, let's suppose one line has a slope m1 and the other line has a slope m2. Obviously, the first line is going to have a positive slope because it's up the hill. The second line is going to have a negative slope because it's down the hill. And we're interested in finding the angle between them. Now, there's some congruency here because these are vertical angles, so these are going to be the same measure. And just visually, we can tell that these angles are acute, which is to say they're less than 90 degrees. The formula that we're going to apply only ever calculates the acute angle that's formed by the intersection of two lines. So this angle, we'll call this alpha. There's also this obtuse angle out here, and then a corresponding vertical angle for that one here. We are not calculating those. So if you ever did want to find the measure of the obtuse angle, you would have to notice that it's supplementary with angle alpha, which is to say that the sum of alpha and this unknown angle out here, let's call it beta, is going to be 180 minus alpha. So the sum of alpha and beta is 180. Let's write that. And if you're interested in alpha, you can use this formula that I'm about to show you. If you're interested in beta, you have to do 180 minus alpha. But anyway, let's focus on alpha, the acute angle. It's going to be the arctan. And I know we haven't talked about trigonometric functions yet, but arctan is the same as the inverse tan. So sometimes you may see this written as tan to the minus 1. And that's actually my preferred way to write it, but I'll stick with arctan because I want to be consistent with the reference handbook. So it's the arctangent of the quantity m2 minus m1 divided by 1 plus m2 times m1. Now you might be looking at this and wondering, hey, if we know m1 is a positive value and m2 is a negative value, the denominator is always going to be the same because it's 1 plus this product. And with the commutative property of multiplication, m2 times m1 is the same as m1 times m2. So we don't have to worry about the denominator. It's going to be what it's going to be. But the numerator is a difference. And if we're subtracting a positive value minus a negative value, we're going to be adding the opposite, so that the numerator is going to be positive. Contrast that with if we actually do it the way it's written here, we're going to do a negative value minus a positive value. It's going to get more negative. So we're actually going to get the opposite value in the numerator depending on the order that we put these two in. So what that means is that this equation is order sensitive. However, we'll see this later when we talk about some of the trig functions. It doesn't really make sense to put an argument into the arctangent function that's negative. So you can do one of two things here. You can either make sure that the numerator turns out to be positive by putting these in the correct order. So in this case, it would be m1 minus m2 is going to work out to a positive value. So that's not what's shown here. The other option is you can just leave it the way it is, calculate it, and then if it turns out to be negative, just disregard the negative sign. So I'll put a little note here to that effect. Disregard negative sign, thereby ensuring that the input into the arctangent function is a positive value, and then you'll get the right answer. And you'll be able to calculate alpha, the measure of the acute angle that's formed by two intersecting lines. And that's a quick overview on everything you need to know about lines.